Hello, everyone. We are working on Chapter 2, Section 2.1 in Statistical Methods for Rates and Proportions. So in this section, we're going to talk about statistical inference for a single proportion and how to break down a hypothesis test. So we're going to look at the binomial probability distribution, and this is when we're interested in the number of successes in a fixed number of trials. So suppose we have that X follows a binomial distribution with the number of trials being N and the fixed probability of success being P. Then we can define the PDF by the probability that X equals X, and that is equal to N choose X, P to the X, Q to the N minus X. So this first piece, the N choose X, tells us the number of combinations possible of having X successes in N trials. And then P is our probability of success raised to the number of successes. Q, our probability of failure, raised to the number of failures, will give us our overall probability. So when we want to go out to set up a hypothesis test, there's a nice paragraph in this section that talks about the breakdown of the steps. And in general, we're going to have 4 steps, which have some parts within it, which are to write out the null and alternative hypotheses. We're going to do that both in notation and in words during our course. We're going to then calculate the probability of observing a test statistic as extreme or more extreme than the one we saw in our sample, assuming the null hypothesis is true, otherwise known as finding the p-value. We're going to make a statistical decision by comparing the p-value to the predetermined significance level alpha, and then we're going to state the conclusions in context of the problem. Now, in general, this gives us a nice format of how to do just one test, asking one single question, and in the later parts of this chapter, we're going to go through confidence intervals. So in hypothesis testing, we are going to have a truth, which is on this left-hand side. Either our null hypothesis is true, H0, or our alternative hypothesis is true, HA. And then on the top gives our statistical decisions. We will either reject H0 or we will fail to reject H0. So in 2 of these spaces, we have a correct decision. If we fail to reject H0 when H0 is true, that's a correct decision. And if we reject H0 when the truth is that HA is true, that's also a correct decision. But there's 2 types of errors that we might make in hypothesis testing. The first type is a type 1 error, and that is also set as our significance level alpha. And that's the probability that we reject H0 given H0 is true. The second type of error we can make is a type 2 error. And we have the probability of a type 2 error being beta. And that happens when we fail to reject H0 when HA is true. So there's not a better or worse type of error to make. It really just depends on the actual situation as to which type of error would be more severe. So here's an example that we worked through during chapter 1. In our example, either the patient does not have the disease or the patient does have the disease. That's HO and HA. And if we reject HO, that may be because we got a positive test on some screening test. And if we fail to reject HO, that would be because the test came up negative. So in 2 cases, we have a correct decision, which we talked about in the last chapter, which would define our specificity and sensitivity of the test, right? Remember, specificity is when we get a negative test given they don't have the disease, and the sensitivity is getting a positive test given you do have the disease. But there might be an error in our test, and that happens when we reject HO, so we find out that they get a positive test, but the patient actually does not have the disease. And that type of error would be a type 1 error. And if we get a negative test, when the patient does have the disease, that would be a type 2 error in this case. So setting up a truth table can be helpful to identify types of errors in our testing. And I hope to see you guys next time. Have a great day.